Hello everyone. Today we will study three-dimensional coordinate system. In general, a real line from negative infinity to infinity, that's a one-dimensional space. It's represented by R. That's a one-dimensional space. A SY plane, a 2D plane with S and Y axis. A 2D plane with S and Y axis, that's called two-dimensional space. It's represented by R2. That's a two-dimensional space. It's represented by R2. Now, in a three-dimensional space, we have three axes. The horizontal axis is called the y-axis. The vertical axis is called the z-axis. The axis going out of the wall. The axis going outward is called the s-axis. The axis going outward is called the s-axis. That's a three-dimensional space. It's called R3. That's a three-dimensional space. It's called R3. Next, let me show you how to plot points. In general, in the real line, in R, every number represents a point. In the real line, every number represents a point. For example, 0 is here. Say number 3 is somewhere on the line. Every number represents a point on the line. In the real line, every number represents a point on the line. In R2, every ordered pair represents a point on the line. In R2, every ordered pair represents a point on the plane, on the SY plane. Ordered pair means a pair of number. For example, 2, 1. Ordered pair, every ordered pair represents a point on the SY plane. In R2, every ordered pair represents a point. Ordered pair means for this pair of number, the order matters. 2, 1 and 1, 2, they are different, they are not the same. So in R2, every ordered pair represents a point on the plane. Similarly, in R3, we use 3 numbers to represent a point. Every ordered triple represents a point. In R3, every ordered triple represents a point in a three-dimensional space. That means in R3, we use a triple of number to represent a point. In order to plot points in R3, let me first review how to plot points in R2. In R2, plot points (1, 2) and 3, -1. Let's plot these 2 points in R2 first. In R2, that's the s-axis, that's the y-axis. Point 1, 2. We first will plot x first. S coordinate is 1. Then y coordinate is 2. we move up 2 units from here. 1, 2. That's the point 1, 2. So second point 3, 1, 3, -1. S coordinate is 3. We first of all count 3 units from S-axis. 1, 2, 3. Then Y coordinate is -1. We go down by 1 unit. That's the point 3, -1. So we first of all plot S coordinate first. Then go up by 2 units for Y coordinate. For the other point, we plot S coordinate first. Then go down by 1 unit. We get a point 3, -1. That's how we plot points in R2. Now in R3, it's very similar. In R3, plot points 1, 2, 3, and 3, -1, -2. In R3, plot points 1, 2, 3, and 3, -1, -2. Let me show you how to plot the first point 1, 2, 3. These 3 numbers 1, 2, 3, 1 represent S coordinate, 2 represent Z coordinate, sorry, Y coordinate, 3 represent Z coordinate, S, Y, Z. Let's draw the coordinate first. That's the S, Y, and Z axis. The direction going outward toward the plane. The direction going outward, that's the positive S-axis. That's the positive direction of S-axis. The horizontal direction going to the right. Horizontal axis going to the right, that's the positive Y direction. The vertical axis going upward, that's the positive Z direction. That's positive S-axis. That's the negative S-axis. That's going into the wall. That's the positive Y-axis. This is the negative Y-axis. And this is the negative Z-axis. Now let's plot the first point. 1, 2, 3. We usually plot 1, 2 in the SY plane first. Plot 1, 2 in the SY plane first. So S coordinate is 1. Y coordinate is 2. That's the point 1, 2 in the SY plane. S coordinate is 1. Y coordinate is 2. That's the point 1, 2 in the SY plane. Now Z coordinate is 3. We move up by 3 units. Z coordinate is 3. Move up by 3 units. Z coordinate is 3. So we try to move up by 3 units. Start from this point, move up by 3 units. That's the point 1, 2, 3 in R3. So we first of all plot point 1, 2 in the SY plane. When Z coordinate is 3, move this point up by 3 units. That's the point 1, 2, 3. How do we plot the other point? 3, -1, -2. Let's do the same thing. Draw the coordinate plane first. That's the positive Z-axis. That's the positive Y-axis. That's the positive S-axis. That's the negative Y-axis. That's the negative S-axis. That's the negative Z-axis. S coordinate is 3. Y coordinate is -1. S coordinate is 3. 1, 2, 3. Y coordinate is -1. So that's positive Y direction. This is negative Y direction, somewhere here. Then the point -1, comma 3 somewhere here. That's the point 3, comma -1 in the xy plane. That's the point 3, comma -1 in the xy plane. Then here the z coordinate is -2. Z coordinate is -2, so I go down by 2 units. Go down by 2 units. Let me make an x-axis a little longer. Shift this point down by 2 units. So that's the point 3, comma -1, comma -2. We first of all plot point 3, comma -1 in the xy plane. Then when z coordinate is -2, I shift this point down by 2 units. That's the point 3, comma -1, comma -2. Next, I'll show you how to use equations to represent graphs in R3. First of all, let me review everything in R2. What does s equal to 1 represent in R2? What does s equal to 1 represent in R2? In R2, s equal to 1 represent all points in the xy plane that satisfies this equation. So when s equal to 1, y could be 0, y could be 1, y could be 2, y could be 3, y could be -1, -2, and so on. So all these y values together form a vertical line. This line represents the equation s equal to 1. So in R2, the equation s equal to 1 represents a vertical line. Represent a line perpendicular to the x-axis. Passing through number 1 in the x-axis. So in R2, s equal to 1 represents a line perpendicular to the x-axis, passing through 1 in the x-axis. Another example. What does y equal to 2 represent in R2? What does the equation y equal to 2 represent in R2? So in the xy plane, y equal to 2 represents the set of all points that satisfy the equation y equal to 2. Y equal to 2 is here. Then when y equal to 2, s could be 0, s could be 1, s could be 2, s could be 3, s could be -1, -2. Connect all these points together, we have a vertical line, we have a horizontal line here. This line represents the equation y equal to 2. So in R2, the equation y equal to 2 represents a line perpendicular to the y-axis. and passing through number 2 in the y-axis. The equation y equal to 2 represents a line perpendicular to the y-axis and passing through number 2 in the y-axis. Next, what does s equal to 1 represent in R3? What does s equal to 1 represent in R3? S equal to 1 represents a set of all points that satisfy the equation s equal to 1. So that's an s-axis, that's the y-axis, that's the z-axis. S equal to 1, 1 is here in the s-axis. What does s equal to 1 represent in R3? It represents a set of all points that satisfy this equation s equal to 1. That means when s equal to 1, y could be 1, y could be 2, y could be 3. At the same time, z could be 1, z could be 2, z could be 3. And when y is 1, z could be 1, z could be 2, z could be 3. When y is 2, z could be 1, z could be 2, z could be 3. When y is 3, z could be 1, 2, or 3. The set of, you can see the set of all these points form a plane here. The set of all these points form a plane here. This plane is perpendicular to the s-axis. The set of all these points form a plane here. This plane is perpendicular to the s-axis and passing through number 1 in the s-axis. Here in R3, the equation s equal to 1 represents a plane perpendicular to the s-axis. This plane is perpendicular to the s-axis. Perpendicular to the s-axis. Or you can say it's parallel to the YZ plane. We can say it's parallel to the YZ plane. And passing through the point passing through number 1 in the s-axis. Here s equal to 1 represents a plane perpendicular to the s-axis. Or you can say perpendicular to the s-axis is the same as saying parallel to the YZ plane and passing through number 1 in the s-axis. Next example. What does the equation y equal to 2 represent in R3? This equation y equal to 2 represents the set of all points that satisfy this equation in R3. Let me draw the three-dimensional coordinate system first. This is the s-axis. This is the y-axis. This is z-axis. Y equal to 2. 2 is somewhere here in the y-axis. Now, when y equal to 2, x and z could be any values. S and z could be any values. It's possible that s could be 1, s could be 2, s could be 3. And at the same time, z could be 1. When z is 1, s could be 1, s could be 2, s could be 3. Z could be 2. When z is 2, s could be 1, could be 2, or it could be 3. We see that the set of all these points form a plane here. The set of all these points form a plane here. So the equation y equal to 2 represents a plane perpendicular to the y-axis passing through 2. It represents a plane perpendicular to the y-axis and passing through 2 in the y-axis. So in R3, the equation y equal to 2 represents a plane passing through. It presents a plane perpendicular to the y-axis. Perpendicular to the y-axis. Perpendicular to the y-axis, which means it's parallel to the SC plane. Parallel to the SC plane. Passing through number 2 in the y-axis. Next. What does the equation z equal to 3 represent in R3? What does the equation z equal to 3 represent in R3? So z equal to 3, this equation z equal to 3 represents the set of all points that satisfies this equation in R3. Let me show you the picture. Assume that's the S, Y, Z axis. 3 is here in the Z axis. 1, 2, 3. Suppose that's number 3 in the Z axis. When Z equals 3, S and Y could be any values. So when Z equals 3, it's possible that S is 1, S is 2, or S is 3. And at the same time, it's possible that Y could be 1. When Y is 1, S could be 1, S could be 2, S could be 3, Y could be 2. When Y is 2, S could be 1, S could be 2, S could be 3, and Y could be 3. When Y is 3, S could be 1, S could be 2, S could be 3. So we can see that here, the set of all these points form a plane. The set of all these points form a plane. The set of all these points form a plane. This plane is perpendicular to the z-axis and passing through number 3 in the z-axis. This plane is perpendicular to the z-axis and passing through number 3 in the z-axis. So in R3, z equal to 3 represents a plane. Z equal to 3 represents a plane. Perpendicular to the z-axis. Perpendicular to the z-axis which means it's parallel to the xy plane. Passing through the point, passing through number 3 in the z-axis. Passing through number 3 in the z-axis. So in R3, the equation z equals 3 represents a plane perpendicular to the z-axis, which means it's parallel to the xy plane, passing through number 3 in the z-axis. Next example, what does the inequality x greater than 4 represent in R2 and R3? In both R2 and R3, this inequality x greater than 4 represents the set of all points whose x coordinate is greater than 4. Now let me show you the pictures in R2 first. In R2, the picture looks like this. That's an x-axis, that's an y-axis. So number 4 is here in the x-axis. And this is a line, s equal to 4. For all points to the right side of this line, its x coordinate is greater than 4. So s greater than 4 represents the set of all points to the right side of the line, s equal to 4. The set of all points to the right side of the line, s equal to 4. So in R2, s greater than 4 represents the set of all points to the right of the line, s equal to 4, not including the line itself. Not including the line itself. So it represents the set of all points to the right of this line, s equal to 4, not including this line itself. Now let me show you the picture in R3. In R3, that's the z-axis. That's the y-axis. This is the x-axis. This is the x-axis. Assume number 4 is somewhere here in the x-axis. Assume that's number 4 in the x-axis. So x greater than 4 represents the set of all points whose z coordinate is greater than 4. So everything go in front of 4 will have larger x-axis. At all points go in front of 4 will have larger x-axis. So assume that's the plane s equal to 4. Assume that's the plane s equal to 4. Assume that's the plane s equal to 4. The inequality s greater than 4 represents the set of all points in front of the plane. The set of all points in front of the plane s equal to 4. The set of all points in front of the plane s equal to 4. the set of all points in front of a plane s equal to 4. So in R3, s greater than 4 represents the set of all points in front of the plane s equal to 4, not including the plane. It's a set of all points in front of the plane s equal to 4, but not including the plane itself, because there's no equal sign. So s greater than 4 represents a set of all points in front of the plane s equal to 4, not including the plane itself. Next, what does the inequality y less than or equal to negative 2 represent in R3? We know that in general, this inequality represents a set of all points that satisfies that y is less than or equal to negative 2, which means the set of all points whose y coordinate is less than or equal to negative 2. Let me show you the picture. That's x-axis, that's the y-axis, that's the z-axis. This way is in the positive y direction. So this will be negative y direction. 0 is here, negative 1, negative 2, assume negative 2 is here. Assume negative 2 is here. Let me draw a plane y equal to negative 2. Assume that's the plane y equal to negative 2. Assume this is a plane y equal to negative 2, which is a plane perpendicular to the SC plane and passing through negative 2 in the y-axis. That's a plane perpendicular to the y-axis and passing through negative 2 in the y-axis. Assume this is a plane y equal to negative 2. If y coordinate is less than negative 2, we know that the set of all points to the left side, the set of all points to the left side, for the set of all points to the left side, their y coordinate will be less than negative 2. Negative 3, negative 4, negative 4, and negative 6. The set of all points to the left side, their y coordinate will be less than negative 2. So it represents a set of all points to the left side of the plane. It represents a set of all points to the left side of the plane, including the plane y equal to negative 2. The set of all points to the left side of the plane y equal to negative 2, including the plane y equal to negative 2. In R3, y less or equal to negative 2 represents the set of all points to the left of the plane y equal to negative 2, including the plane itself. including the plane y equal to -2. This inequality represents the set of all points to the left side of the plane y equal to -2, including the plane itself. Next example. What does the inequality g greater or equal to -1 represent in R3? What does the inequality g greater than or equal to -1 represent in R3? In general, this inequality represents a set of all points which satisfies that g is greater than or equal to -1. That means the set of all points whose g coordinate is greater than or equal to -1. That's the z-axis. Let me draw the plane g equal to -1 first. That's g equal to -1. Let me first of all draw a plane g equal to -1. Assume that's the plane g equal to -1. For all points above this plane, their g coordinate is greater than or equal to -1. So this inequality g greater or equal to -1 represents a set of all points above the plane g equal to -1, including the plane itself. The set of all points above the plane g equal to -1, including the plane itself. The set of all points above the plane g equal to -1, including the plane itself. So in R3, the inequality g greater or equal to -1 represents the set of all points above the plane g equal to -1, including the plane itself. Next example. What does this equation x squared plus y squared equal to 4 represent in R3? In general, it represents a set of all points that satisfies this equation. And this equation in R2 we know is a circle, center and origin with radius 2. And in this equation here, g component is missing. That means this equation doesn't depend on g. For all g value, the picture is the same. So when g equal to 0, we have a circle, center and origin with radius 2. When g equal to 1, we get the same circle, center and origin with radius 2. When g equal to 2, we get the same circle, center and origin with radius 2. When g equal to -1, we get the same circle. When g equal to -2, we get the same circle. Connect all these circles together. If we connect all these circles together, the graph is a cylinder. If we connect all these circles together, the graph is a cylinder. If we connect all these circles together, the graph is a cylinder. So x squared plus y squared equal to 4 in R3 represents a cylinder centered at the z-axis with radius 2. Its graph is a cylinder centered at the z-axis with radius 2. Next example. What does the equation z equal to x squared represent in R3? What does the equation z equal to x squared represent in R3? We know that this equation doesn't depend on y. When y is 0, we have a graph z equal to x squared, which is a parabola open upward. When y equal to 0, we have a parabola in SC plane. When y equal to 0, z equal to x squared is a parabola in the SC plane. When y equal to 1, this picture doesn't depend on y. So when y equal to 1, we get the same picture. We get exactly the same picture when y equal to 1. When y equal to 2, we get the same picture. When y equal to -1, -2, we get exactly the same picture. If we connect all these parabola together, we have a surface here. If we connect all these parabola together, we have a surface. If we connect all these pictures together, we have a surface here. That's the z-axis. This is the y-axis. This is the x-axis. The graph is a surface perpendicular to the xc plane and passing through the curve z equal to x squared in the SC plane. So in R3, z equal to x squared represent a surface perpendicular to the SC plane. And passing through the curve. G equal to S squared in the SC plane. It represents a surface perpendicular to the SC plane and passing through the curve G equal to S squared in the SC plane. Next example. What does G equal to half of Y represent in R3? We know that in general, it represents a set of all points that satisfies this equation, G equal to half of Y. But here in this equation, the S component is missing, and G equal to half of Y is a line in the SC plane. That means when S equal to 0, we get a line. When S equal to 1, we get the same line. When S equal to 2, we get the same line. So when S equal to 0, we get a line, G equal to half of Y. When S equal to 1, we get exactly the same line, G equal to half of Y. When S equal to 2, we get the same line, G equal to half of Y. When S equal to 3, we get the same line, G equal to half of Y. So connect all these points together. We have a plane here. Connect all these points together, we have a plane here. If I connect all these lines together, that's a plane. So the graph of in R3, G equal to negative half represents a plane perpendicular to the YG plane. It's a plane perpendicular to the YG plane and passing through the line G equal to half of Y in the SC plane. In the YG plane, This equation represents a plane perpendicular to the YG plane and passing through the line G equal to half of Y in the YG plane. This line is G equal to half of Y. Next, let me show you how to find distance between 2 points. Let P equal to x1, y1, z1, and Q equal to s2, y2, z2 be 2 points. In R3. Then the distance distance between points P and Q is defined as distance between P and Q equal to what? We can try to use Pythagorean theorem to find it. Assume that's point P with coordinates x1, y1, z1. Assume that's point P, coordinates x1, y1, z1. Assume that's point Q with coordinates x2, y2, z2. Let's near distance. The diagonal of this box is near distance. The diagonal of this box is near distance. And these three sides, this is change of x. This is a change in x direction. This is change of x. This side is change of y. And this side is change of z. That's a change in z direction. That's a change in y direction. That's a change in x direction. Now, how do we find their distance? Look at this rectangle in the bottom first. Look at this rectangle in the bottom first. If I draw a diagonal on the bottom, let me call this side T. Then this is a right triangle. We have T squared equal to delta S squared plus delta Y squared. This is a right triangle. We have T squared equal to delta S squared plus delta Y squared. Now, next, assume the distance between point PQ is D. Let me call it diagonal D. Then this side, D, T, delta Z, this form a right triangle. Because this edge is perpendicular to the entire plane on the bottom. So it's perpendicular to this line here. This form a right triangle. These three sides, D, T, delta Z form a right triangle. So D squared is T squared plus delta Z squared. D squared is D squared equal to T squared plus delta Z squared. Then if I plug in T squared is delta X squared plus delta Y squared plus delta Z squared. So D can be written as square root of delta X squared plus delta Y squared plus delta Z squared. When we take square root, in general, answer should be positive or negative. But distance represents distance. Distance is always positive. So don't drop negative sign. D equal to square root of delta X squared plus delta Y squared plus delta Z squared. That's the distance between point P and Q. And what's delta X, delta Y, delta Z here? Change of X is X2 minus S1. Change of X here is X2 minus S1. Change of Y is Y2 minus Y1. And change of Z is Z2 minus Z1. Then we can plug in. Delta X is S2 minus S1 square. Delta Y is Y2 minus Y1 square. Delta Z is Z2 minus Z1 square. So that's the distance between point P and Q. That's the distance between point P and Q. So distance between point P and Q is defined as square root of S2 minus S1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's the distance formula for distance between 2 points. x2 minus s1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's the distance between 2 points, P and Q. Next, let's try a simple example. Let P equal to 1, -2, 3, and Q equal to -2, -1, 1. Be points in R3. Find distance between point P and Q. Find distance between point P and Q. So use the distance formula. Distance between point P and Q is square root of x2 minus s1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's -3 squared is 9. -1 plus 2 is 1. 1 squared is 1. 1 minus 3 is -2. -2 squared is 4. 9 plus 1 plus 4 is 14. So the distance between point P and Q is square root of 14. Next, let me show you how to define sphere in R3. Let O equal to x0, y0, z0. Let O be a point in R3. And let R be a real number. Let R be a real number with R greater than 0. That means R is a positive real number. Then a sphere in R3 is defined as the set of all point P the set of all point P in R3 such that distance between OP equal to R. Note, in this definition, of sphere, O is called the center of the sphere. And R is called the radius of the sphere. Next, let me show you how to find equation of a sphere. We know that distance between OP is always equal to R for any sphere. The distance between OP is always equal to R. Distance between O and P, here we use distance formula. That's square root of y2 minus y1. Sorry, s2 minus s1, y2 minus y1, and z2 minus z1. So distance between OP is square root of s2 minus s1, which is s minus x0 squared, plus y2 minus y1, which is y minus y0 squared, plus z2 minus z1, which is z minus z0 squared, equal to R. If I square both sides, I have x minus x0 squared, plus y minus y0 squared, plus z minus z0 squared equal to R squared. This is called the equation of a sphere. This is called the equation of a sphere. In this equation, x0, y0, z0 is the center of the sphere. And R is the radius of the sphere. And the picture of a sphere looks like this. So that's the center O. Radius is R everywhere. So this is R. This is also R. This is also R. Assume the center O is x0, y0, z0. Then the equation of this sphere is s minus x0 squared plus y minus y0 squared plus z minus z0 squared equal to R squared. That's how the picture looks like. Next, let's do a simple example. Show that this equation s squared plus y squared plus z squared equal plus z squared minus 4x plus 6y minus 8z minus 7 is the equation of a sphere. And find the center and the radius of the sphere. Show that this equation is the equation of a sphere, and find the radius, find the center and the radius of the sphere. So, in order to show this is the equation of a sphere, we must write this equation in this form. We must rewrite this equation in this form. So, in order to write this equation in this form, we try to complete squares. So I try to group x together, s squared minus 4x. Group y together, y squared plus 6y. Group z together, z squared minus 8z. Move the constant to the other side. equal to positive 7. Then we try to complete squares. I try to add a term here to make this a perfect square. In general, to decide what to add, take the middle number, divide by 2, then square. 4 divided by 2 is 2. 2 squared is 4. So add 4 to both sides. Take the middle number, divide by 2, then square. 6 divided by 2 is 3. 3 squared is 9. Add 9 to both sides. 8 divided by 2 is 4. 4 squared is 16. Add 16 to both sides. So add 4 to both sides, add 9 to both sides, add 16 to both sides. Then complete square. How do we complete square here? Find two numbers. Let them multiply to be 4. Add to be negative 4, which is negative 2, negative 2. That's s minus 2 square. Find two numbers. Let multiply to be 9. Add to be 6. We have positive 3, positive 3. We get y plus 3 square. Find two numbers. Let multiply to be 16. Add to be negative 8. And that should be negative 4, negative 4. I get z minus 4 square. Equal to 7 plus 4 is 11. 11 plus 9 is 20. 20 plus 16 is 36. So this equation can be rewritten as x minus 2 square plus y plus 3 square plus z minus 4 square equal to 6 square. Let match in the form. Let match in the equation of a sphere. So this is the equation of a sphere. The center is 2, negative 3, and 4. The center is 2, negative 3, and 4. The radius is 6. Next, we will study vectors. First of all, let me introduce what is a vector. A vector is a quantity that has direction and magnitude. Let me show you a picture first. Assume that's a vector. Assume that's a vector. By drawing a vector, we know the direction. This is the direction of the vector. By drawing a vector, we know the direction. The magnitude of the vector is the length of the vector. The magnitude of the vector is the length of the vector. That's the magnitude of the vector. So by drawing a vector, we know the length, we know the direction of the vector. The magnitude is the length of the vector. Next, let me show you some operation about vectors. In general, there are two operations about vectors, called vector addition and scalar multiplication. Note, in general, there are two operations about vectors. Called vector addition and scalar multiplication. Let me show you some examples. Let vectors u, v, w be defined as the following vectors. Let vectors u, v, w be defined as the following. Assume that's vector u. Assume that's vector v. Assume that's vector w. Find each of the following vectors. How do we find a vector u plus v? How do we find a vector u plus v? In order to find u plus v, I draw first vector u first. I draw vector u first. Make sure same direction, same length. That's vector u. Then next, draw vector v. Put the tail of vector v on the head of vector u. Draw vector v. Put the tail of vector v on the head of vector u. Shift vector v here. Make sure the same length, same direction. This is vector v. Then connect the original tail and the final head. This is the vector u plus v. This is a vector u plus v. This vector represents u plus v. U plus v. That's how we add two vectors. How about u plus v plus w? How do we add three vectors? U plus v plus w. We draw vector in orders. U first, vector u first. Shift vector u here. Shift vector u here. Make sure the vector point in the same direction with the same length. Then plus vector v. We put the tail of vector v on the head of vector u. Shift vector u, shift vector v here. Put the tail of vector v to the head of vector u. That's vector v. Then plus vector w. Shift vector w here. Shift vector w here. Make sure the tail of w connect to the head of vector v. Shift vector w here. Make sure the tail of w touch the head of vector v. Make sure the same length, same direction. That's vector w. Then connect the initial tail with the final head. Connect the initial tail with the final head. This vector here is u plus v plus w. This vector represents u plus v plus w. Next, how do we compute 2u? How do we compute 2u, 3u? How do we compute 2u and 3u? Let me draw vector u first. Assume that's vector u. 2u represent a vector pointing in the same direction, but the length is twice of vector u. This is vector 2u. This is vector 2u. It points in the same direction as vector u, but the length is twice as long as vector u. This is one vector. This is one vector. It points in the same direction as vector u, but the length of the vector is twice as long as vector u. Now for 3u, it's the same thing. It's a vector pointing in the same direction of vector u, but the length is 3 times as many as vector u. It's the same vector. It's a vector pointing in the same direction as vector u, but the length is 3 times as long as vector u. How about negative u? How about negative vector u? Negative vector u can be written as -1 times u. So if net vector u, -1u is a vector that points in the opposite direction as vector u. This is negative u. Suppose next vector u. This is negative vector u. This is the same vector pointing in the opposite direction as vector u. How about -2u? -2u is the vector. Suppose that's vector u. -2u is a vector that points in the opposite direction of vector u, but it's twice as long as vector u. This is -2u. It's a vector pointing in the opposite direction of vector u, but it's twice as long as vector u. Next, let me show you some more operation here. How can we calculate 2u plus 3v? How can we calculate 2u plus 3v? So let me copy vector u and v here first. That's vector u. That's vector v. Let's draw 2u first. 2u is a vector pointing in the same direction as vector u, but it's twice as long as vector u. This is vector 2u. How about 3v? 3v is a vector that points in the same direction as vector v, but it's 3 times as long as vector v. That's vector 3v. Then 2u plus 3v. Draw 2u first. This is vector 2u. Then S3v. Shift vector 3v here. Shift the tail of 3v to the head of 2u. Shift the vector here. This is vector 3v. Then connect the initial tail with the final head. This is the vector 2u plus 3v. This is a vector 2u plus 3v. Now, we know that there's no vector subtraction, but we can define subtraction in the following way. There's no vector subtraction, but we can define subtraction in the following way. U minus v can be defined as u plus -1 v. That's a scalar multiplication and that's a vector addition. So we can define subtraction in this way. U plus -1 v. That's called scalar multiplication, and that's called, this is vector addition. So we define subtraction using scalar multiplication and vector addition. Now how do we compute u minus v? How do we compute u minus v? We can compute, let's draw vector u first. Let me shift vector u here. This is vector u. Let me shift vector v here. This is vector v. Then negative v. -1v point in the opposite direction as vector v. -1v point in the opposite direction as vector v, but the length is the same. Then we do addition. Draw vector u first. Shift this vector, copy here. That's vector u. Plus -1v plus -1v. Shift the tail of vector v to the head of vector u. Then connect the initial tail to the final head. This vector here is u minus v. This vector here is u minus v. How about u minus w? Same thing, write it as u plus -1 w. Let me copy vector u and vector w first. This is vector u. Vector w is this one. Let me shift it here. Make sure the length is the same and point in the same direction. Assume that's vector w. -1 times w is the same vector but point in the opposite direction. The length is the same but it's pointing in the opposite direction. This is -1 times w. This is -1 times w. Then we take vector u plus -1 times w. That's vector u. That's -1 times vector w. And this vector, this new vector here, connect the initial tail to the final head. This vector is u minus v, u minus w. This vector is vector u minus w. Connect the initial tail to the final head here. Next, let me show you components of vectors. Let A equal to x1, y1, z1, and B equal to s2, y2, z2 be 2 points in R3. Let A and B be 2 points in R3. Vector AB is defined as vector AB equal to S2 minus S1, comma, Y2 minus Y1, comma, Z2 minus Z1. Assume A and B are 2 points in R3. That's point A, that's point B. If we connect point A, if I join point A and point B, I have a vector here. If I join point A and B, I have a vector. This vector is called vector AB. An arrow on the top represents vector. An arrow on the top represents vector. This represents vector AB, where A is called the tail, B is called the head of the vector. A is called the tail, B is called the head of the vector. Vector AB is defined as head minus tail. Vector AB is defined as head minus tail. So use B is the head, A is the tail. Use head minus tail. X2 minus S1, Y2 minus Y1, Z2 minus Z1. Head minus tail is vector AB. In general, we use parentheses to represent points. Use parentheses to represent points, and use angle bracket to represent vectors. That's how we define vector AB. Next, let's look at a simple example. Let A equal to 2, -3A, and B equal to -2, 1, 4, be 2 points in R3. Find vector AB and BA. Find vectors AB and BA. So for vector AB, A is the tail, B is the head. Use head minus tail. A is the tail, B is the head. Head minus tail. -2 minus 2 is -4. 1 minus -3 is +4. 4 minus A is -4. That's vector AB. How about vector BA? In vector BA, B is the tail, A is the head. In vector BA, B is the tail, A is the head. Use head minus tail. Use point A minus point B. I have 2 minus -2, which is 4. -3 minus 1, which is -4. A minus 4, that's 4. That's vector BA. Next, let me show you the magnitude of a vector. Magnitude, sometimes it's called a length. Or norm. Magnitude sometimes is called length or norm. Magnitude of a vector. How do we find the magnitude of a vector? Let V be vector V1, V2, V3. The magnitude of vector V. The magnitude of vector V is defined as with 2 bars represent magnitude of vector V. that equal to square root of v1 square plus v2 square plus v3 square. The reason is because of Pythagorean theorem. The reason is because of Pythagorean theorem. Also, keep one idea in mind. For all points A, B, distance from point A to B is the same as the magnitude of vector AB. For any points A and B, distance from point A to point B is the same as the length of the vector AB. Distance from A to B is the same as the magnitude of vector AB. Keep this idea in mind. Next, I'll show you some operations about vectors. We know that in any vector space, we always have two operations called vector addition and scalar multiplication. Next, let me show you how we use it here. Vector addition and scalar multiplication. Let vector u be u1, u2, u3, and vector v be v1, v2, v3, be two vectors. In R3. And let k be any scalar. Let k be a scalar. A scalar means a real number. Let k be a scalar. A scalar means a real number. We define vector addition like this. U plus v. Vector addition, u plus v is u1 plus v1, u2 plus v2, u3 plus v3. That's called vector addition. Scalar multiplication, ku is defined as k times the first component of u, ku1, then k times the second component of u, ku2, k times the third component of u, ku3, which says we distribute k into vector v. We distribute k into vector v. This is called scalar multiplication. This is vector addition. This is scalar multiplication. Even though in a vector space there's only two operations, vector addition and scalar multiplication, we can do subtraction and division in the following ways. Note, keep this idea in mind. If we try to do subtraction for u minus v, we can write it as u plus -1 times v, which is u1, u2, u3 plus -1 times v. V has components v1, v2, v3. Then here we do scalar multiplication first. I take -1 times vector v. I get u1, u2, u3 plus -v1, distribute -1. I get -v1, -v2, -v3. Then add the vectors. u1 plus -v1 is u1 minus v1. u2 plus -v2 is u2 minus v2. u3 plus -v3 is u3 minus v3. So for subtraction, we can also do the same thing. U minus v. Vector u minus v is u1 minus v1. Subtract the first component, subtract the second component, u2 minus v2, u3 minus v3. That's how we define subtraction using scalar multiplication and vector addition. That's how we define subtraction using these two operations. Now, how about division? Suppose we have u divided by k, assume k is not 0. Suppose we have vector u divided by k, assume k is not 0. We can write it as 1 over k times vector u. U over k, I can write it as 1 over k times vector u. And we know that the component for vector u is u1, u2, u3. The component for vector u is u1, u2, u3. Then distribute 1 over k into the vector. That's scalar multiplication. Distribute 1 over k. We have 1 over k times u1, comma 1 over k times u2. One over k times u3. According to the rule of scalar multiplication, I distribute 1 over k into the vector. That can be written as u1 over k, comma u2 over k, comma u3 over k. That's how we define division based on scalar multiplications. That's how we define division based on the scalar multiplications. So keep this in mind. U over k is u1 over k, u2 over k, u3 over k. We take each component, divide by k. Assuming k is not 0, take each component, divide by k. So we have two operations, vector addition and scalar multiplication. We can define subtraction using vector addition and scalar multiplication. We got this formula, and we can define division using scalar multiplication. We got this. So keep this formula in mind. Those are the standard operations. Those are operations derived using these two operations. Next, let's do some simple calculations. Let u equal to 2, 1, 3, and v equal to 4, negative 2, 1 be two vectors in R3. Part A. Find the magnitude of vector u and the magnitude of vector v. Find the magnitude of vector u and vector v. So, magnitude of vector u is square root of 2 square plus 1 square plus 3 square using Pythagorean theorem. By Pythagorean theorem, we have 2 square plus 1 square plus 3 square. That's square root of 4 plus 1 plus 9. That's square root of 14. That's magnitude of vector u. Now for magnitude of vector v, do the same thing. We have square root of 4 square plus negative 2 square plus 1 square by Pythagorean theorem. Square root of 4 is 16. Square root of negative 2 is 4. Square of 4 square is 16. Negative 2 square is 4. 1 square is 1. That's square root of 21. Part B. Find 3u plus 2v and 2u minus v. 3u plus 2v, we have 3 times vector u, 2, 1, 3, plus 2 times vector v, which is 4, negative 2, 1. Then, when we're doing scalar multiplication, distribute first. Distribute 3 into the vector. We have 6, 3, and 9, plus a, negative 4, and 2. Then we add the vectors. 6 plus a is 14. 3 plus negative 4 is negative 1. 9 plus 2 is 11. That's 3u plus 2v. This vector is 3u plus 2v. Now next one. 2u minus v. U is 2, 1, 3. V is 4, negative 2, 1. We do scalar multiplication first. Distribute 2. We have 4, 2, and 6 minus 4, negative 2, 1. When we're doing subtraction, we subtract each component individually. Subtract each component individually. 4 minus 4 is 0. 2 minus negative 2 is 4. 6 minus 1 is 5. This vector is 2u minus v. Part C. Find vector u plus 2v over 3. Vector u plus 2v over 3. We can do an operation here first. Do the numerator first. Vector u is 2, 1, 3 plus 2 times vector v, which is 4, negative 2, 1. Then do scalar multiplication. Distribute 2 into the parentheses. We have a, negative 4, and 2. Then add the vectors. When we're doing addition, we add each component individually. Here we have 10, negative 3, and 5 over 3. Then when we're doing division, take each component, divide by 3. Take each component, divide by 3. We have 10 divided by 3 is 10 over 3. Negative 3 divided by 3 is negative 1. 5 divided by 3 is 5 over 3. So this is the vector u plus 2v over 3. Next, let me introduce some properties of vectors. For vectors, we have the following properties. First one, vector u plus v is always the same as vector v plus u. That's called a commutative law. Commutative law. Vector u plus v is always the same as vector v plus u. Next one, vector u plus v plus w is always the same as vector u plus v plus w. This is called associative law. Next, vector u plus vector 0 is always u. Vector u plus 0 is always u. Keep in mind that vector 0 is always the vector 0, 0, 0 in R3. In R2 is 2 zeros. In R2, vector 0 is 0, 0. In R3 is 0, 0, 0. Next, vector u plus negative vector u is always vector 0. Vector u plus negative vector u is always vector 0. Scalar k times vector u plus v. Scalar k times vector u plus v is the same as ku plus kv. We can distribute scalar k to both vectors. Next, scalar k plus l times vector u. Scalar k plus l times vector u is always ku plus lu. We distribute u to both scalars, ku plus lu. Next, scalar k times l times u. Scalar k times l times vector u is the same as k times l times vector u. Scalar k times l times vector u is the same as k times l times vector u. Last one. 1 times vector u is always the same as vector u. Those are the property of vectors. Next, let me show you 3 special vectors in R3. Notation for 3 special vectors in R3. In R3, we have 3 special vectors. Vector I. I is the vector 1, 0, 0. Vector J. J is the vector 0, 1, 0. Vector K. K is the vector 0, 0, 1. Those are 3 special vectors. We use I, J, K to represent these 3 vectors. Vector I is the vector 1, 0, 0. Vector J is the vector 0, 1, 0. Vector K is the vector 0, 0, 1. These 3 vectors has a name. They are called the standard base in R3. They are called the standard base in R3. Why they are standard? Let me show you an example. It will make more sense for you. Why they are called standard base in R3? Let me show you an example. It will make more sense for you. Let vector A be A1, A2, A3. Then vector A can be written as A1, 0, 0. Plus 0, A2, 0. Plus 0, 0, A3. We write A0, we write A1, A2, A3 in 3 different vectors. So first vector is A1, 0, 0, plus 0, A2, 0, plus 0, 0, A3. We can write vector A in this form. Then in the first vector, I can factor A1 out. If I pull out A1, I have 1, 0, 0. If I pull out A2, I have A2, 0, 1, 0. If I pull out A3, I have A3 times 0, 0, 1. And here we see that this is vector I. So I can write A1 times vector I. This is vector J, so I can write A2 plus vector J. This is A3, this is K, So I can write A3 times vector k, which means for any vector A1, A2, A3, I can write it as A1i plus A2j plus A3k. That's why AJK are called standard bases in R3. For any vector with components A1, A2, A3, I can always write it as first component A1 times vector I plus the second component A2 times vector j plus the third component A3 times vector k. That's why IJK are called standard bases in R3. So keep this idea in mind that for any vectors in R3, I can always write it in terms of vectors I, j, and k using exactly the same component of the vector. Next, let me introduce a special type of vector called union vector. What is a union vector? A union vector is a vector whose magnitude is 1. A union vector is a vector whose magnitude is 1. Next, let me show you how to find a union vector. For any vector u, for any vector A, to find a union vector, in the same direction, we use the formula u equal to vector A divided by its magnitude. We use the formula u equal to vector A divided by its magnitude. Then how do we know this is a union vector? If I do this operation, how do we know this is a union vector? Let's check in this example here. Let A be a vector in R3. And let vector u be defined as vector A divided by its magnitude. Show that vector u is a union vector. Let me try to show that the magnitude of vector u is 1. In order to show u is a union vector, we need to show its magnitude is 1. In order to show u is a union vector, we must show its magnitude is 1. So show that vector u is a union vector. Let's try to show its magnitude is 1. Let A be the vector of components A1, A2, A3. Since vector A is in R3, it has three components. Let A be the vector of A1, A2, A3. Vector u equal to vector A divided by its magnitude. That's A1, A2, A3 divided by magnitude of vector A. That can be written as A1 over magnitude of A, comma A2 over magnitude of A, comma A3 over magnitude of A. Then magnitude of v is square root of a1 over magnitude of a1, magnitude of a square, plus a2 over magnitude of a square, plus a3 over magnitude of a square. If we multiply out, we can see that every fraction here has the same denominator. So it can be written as square root of a1 square plus a2 square plus a3 square over magnitude of vector a square. They all have the same denominator. Denominator is magnitude of a square. Next, when I take square root, in the numerator I have a1 square plus a2 square plus a3 square. In the denominator, since the magnitude is always positive, so square cancels square root, I get magnitude of vector a. And we know that magnitude of vector a is square root of a1 square plus a2 square plus a3 square, which is the same as the numerator. a1 square plus a2 square plus a3 square. Since the top and the bottom looks exactly the same, I can cancel them out. I get 1. So here we see that magnitude of vector u is 1. Since vector u has magnitude 1, vector u is a unit vector. So here we can see that any vector in the form of vector a divided by its magnitude is always a unit vector. And when we take vector a divided by its magnitude, it may be longer, may be shorter, but its deduction is the same. When we take vector a divided by its magnitude, the vector may be longer, may be shorter, but the deduction stays the same. That's why vector u is in the same deduction as vector a. So this formula can find a vector in the same deduction. This formula can find a unit vector in the same deduction. Next, let's do a simple example. Let vector a equal to -2, -3, and 5. Find a unit vector in the same direction. So in order to find a unit vector in the same direction, we find a magnitude for vector a first. Magnitude of vector a is square root of -2 square plus -3 square plus 5 square. -2 square is 4. -3 square is 9. 5 square is 25. 4 plus 9 is 13. 13 plus 25 is 38. That's the magnitude of vector a. Then, for the unit vector in the same direction, we use vector a divided by its magnitude. We use vector a divided by its magnitude, which is the vector -3, -3, and 5 divided by its magnitude. That's -2 over radical 38, comma, -3 over radical 38, comma, 5 over radical 38. That's a unit vector in the same direction of vector a. Another example, let vector b equal to 4i plus 2j minus 3k. Find a unit vector in the same direction. So first of all, let's write vector b. Let's write b in vector form first. B equal to 4i 2j minus 3k. If I write b in this form, that means the component of vector b is 4, 2, negative 3. If we write b in the form of ijk, that means component of vector b is 4, 2, negative 3. Then we can find magnitude of vector b. Use Pythagorean theorem. I have square root of 4 square plus 2 square plus negative 3 square, which is 16 plus 4 plus 9. 16 plus 4 is 20, 20 plus 9 is 29. So magnitude of vector b is square root of 29. Then for the union vector in the same direction, we use vector b divided by its magnitude, which is 4, 2, negative 3 divided by square root of 29, which is 4 over square root of 29, comma 2 over square root of 29, negative 3 over square root of 29. That's the union vector in the same direction of vector b.